Hi. Merry Christmas, Happy Hanukkah, and Happy New Year. We're getting near to the holiday season, and we thought it might be fun to do a project based on bubble lights. Now you're probably familiar with these little bubble light ornaments that you can get online for decorating a Christmas tree. And they've been around for a very long time. When I was a little kid and my parents would decorate the Christmas tree, these were my favorite ornaments. They may be a little cheesy, but just like a lava lamp, you might not want to admit it, they're kind of fun to watch. And so what we're going to do today is I'm going to go through the principles and we're going to show you how to make a bubble lamp that you can't buy. And then, as we usually do here at Tech Ingredients, we're going to kick things up a couple notches. Now, the basic principle, what is a bubble light? It's a very simple system. What it involves is a sealed glass tube that contains a liquid underneath a vacuum. And because of the presence of the vacuum, the liquid inside will boil at much closer to room temperature than it would naturally at atmospheric pressure. The result is that if you apply a small quantity of heat to the proximal end of the tube, the liquid will boil inside, and as the bubbles rise to the other end, they will begin to decrease in size, they will condense, and they will transfer their heat out. If you understand the technology, this is actually very similar to the operation of a heat pipe used to cool computers and electronic instruments. It's basically a closed loop phase transition system for distributing heat. But in this case, it's a lot more interesting to look at. Now, in theory, you could use plain water for this purpose. The problem with plain water is that, number one, it has a relatively high boiling point. In order to get this to boil near room temperature, you need a really good vacuum at the top end. The more important problem with water, though, is that it has a high heat of phase transition. You have to add a lot of heat to change the liquid into a vapor, and you get a lot of heat at the other end. Bottom line is you need a lot more energy to drive a water-based bubble lamp. A much better choice is to use a low boiling point organic solvent that has a low heat of phase transition so that you can get this to operate with much less energy. Now, in theory, you could use methanol, toluene, hexane, acetone, dichloromethane. Any of them would work. But this is an important warning. Don't use any of these other solvents other than dichloromethane. The reason for that is that, as you can see at the top end of these tubes, we're going to be doing some glass work that involves flame. And all of these other solvents are flammable. You don't want to get them close to the flame. Only dichloromethane is safe to use for this purpose. Now, dichloromethane is toxic, just like any of these other solvents. As long as it's contained within the tube, you're fine. But if the tube breaks and this spills, you have to treat it like any other solvent. You don't want to touch the liquid if you can help it. You want to ventilate the room. You don't want to cut yourself in the glass. Don't get it on your skin. Don't inhale it. But as long as it stays inside of the tube, you're perfectly fine. Now, the other problem you have is I can actually get this to start to boil with just the heat of my hand, just a couple of watts. But unless I want to stand there all day, during a party and demonstrating this bubble light, it's nice to have a base that provides a secure mounting for the tube, as well as a source of heat and a source of light. And so we're going to show you how to make the base as well as the glass tube. So the first step is going to be to fabricate the bubble light itself. And so we're going to go over to the glass working station to do that. Now, if you've never done any kind of glass working before, it's a very interesting hobby and you might find it pretty addictive. And this work that we're going to do today is about the simplest way you can get started. It's some of the most basic techniques. The first thing you need is a place to work. And if you don't have a dedicated station for doing this, you can take a regular wooden table, put either some concrete on top of it, or as we did, an aluminum plate that will help to protect the underlying wood from glass that might be very hot, so you don't get any smoke coming up or any burns. In addition, you need to decide what kind of glass you're going to work with. Now, if you're very skilled and have very good equipment, you can work with soda lime glass. It's a very inexpensive glass that's often used with neon tubes. However, it has a very high coefficient of expansion. As you heat it and cool it, it expands a lot and it shrinks a lot. As a result, it's very demanding for technique because you can easily crack it if you don't heat it smoothly and steadily and very carefully. And so a much better way to get started and a much easier glass to work with is a Pyrex-based glass. This is Pyrex tubing. It's sometimes called Simex or Chemex, but it's a borosilicate tube. And because it has a much lower coefficient of expansion, if you heat it unevenly or you put things down on surfaces that could cool them quickly, this won't crack. It's much more forgiving. Now, the other thing you have to be cognizant of is the source of the heat. You can, in theory, do this with a regular blowtorch, like a propane torch or, better yet, a MAP torch, an air fuel torch. I'd not recommend that because the very top temperature of those torches just gets warm enough to be able to work with the glass. It's much better to use a torch that incorporates oxygen and fuel, in this case, an oxygen propane torch. The temperature is way higher than you need and it gives you a lot more flexibility and control. Now, we do a lot of glass working for, say, plasma tubes and neon lights that we're building. And so we got a higher end Bethlehem burner torch, but you can get something at a welding supply location or even a knockoff on eBay for probably 50 or 60 bucks. And I'd recommend going with the oxygen fuel torch. Now, when you take the glass, you're going to get this glass. And it's not expensive. This is about $1.80 in single quantities. You're going to want to cut it or shorten it. Now, in some instances or in some applications, you're not going to need to cut this, or you need a very, very precise cut. If you do, you can use, say, a diamond saw to be able to cut this off very precisely. But much more conveniently, and if you don't have that kind of equipment, it's best to simply crack it, split it, by creating a very small location where the stress will concentrate, a stress concentrator. To do that, use a sharp tool. You can use a jeweler's file, or better yet, use a carbide glass cutter. This little Speedy Sharp was about $8 or $9 online from eBay. And this thing, it works very well because the insert at the end is carbide. Whenever you hear the word carbide, you really mean tungsten carbide. It's extremely hard. And because of the square edge here, if you tip this a little bit when you cut, you're cutting or you're scratching with this corner or edge of the insert, and you'll create that stress riser. Now, I'm going to shut up for a second, and I want you to be able to hear. I'm going to bring my microphone real close. The sound that this makes when it cuts, it's very typical, and it's the sound that you want to hear when you're making a good scratch. So I'm going to lean down here, and I'm going to make a little bit of a score or a scratch in the tube. Listen. Now, I made a lot of slices back and forth. You don't need to do that. One or two is enough, but I wanted you to be able to hear it. The next step, I don't understand why this works, but it really does. In order to get this to split effectively, you want to wet that scratch. It works. Don't know why, but it does. Then you want to turn the scratch away from your body, so it's facing away from you. And then you want to place your thumbs, let's see if I can find this, yes, place your thumbs directly behind the scratch so that you push against where the scratch is located. And then just give it a snap like that. It's that easy. Now, if you're scared of getting your fingers near the cut, do not put your hands way back here thinking you're going to protect them. You'll probably shatter the tube in about 5 or 6 places and actually have a much greater likelihood of cutting yourself. If you're really scared the first couple of times you do this, put on a pair of gloves. Just make sure that you approximate your thumbs when you do that snap. It's really easy and you get a really good cut. It works very well. Now the next thing that you have to do is you're going to have to close up the end of the tube. If you look at this finished tube here, you'll see that what we've made is what looks like a very tall test tube out of this end of the tube. And in order to close that off, you could, in theory, heat this up with the torch and just use either a piece of graphite like this, which is an unfinished rocket nozzle, or a piece of wet wood or anything else, and as you get it hot, you could kind of try to work it in to close off the end of the tube. It's a lousy way to do it because what will happen is you'll often distort the end of the tube, maybe even mushroom it out a little bit. And when we mount this, we want a very close fit with the inside diameter of the hole so we get good heat transfer from the heat source. So the better way to close this off is to actually draw the end down. What you do is you put this in the flame like this, and you're going to literally draw the ends closed. The problem with doing it just like that is that in order to not burn my hands, I have to work pretty far up from the end here. And so what we're going to do when I get this thing started up, I'm going to turn on the fuel, is we're going to use a little technique that'll save a lot of glass. Let me just get the tanks going. Turn the oxygen on and off only after the fuel has been turned on. So we start by turning on the fuel, and now we add the oxygen. And when you want to turn the oxygen off, you turn it off first. Otherwise you get a really loud pop. It's kind of scary. So let's get a little oxygen going here. And we'll see a nice blue flame. Put on my little sunglasses here. It makes it a little easier. It just makes it a little dimmer because this can get a little bright. Now, the trick I'm going to use to save some glass rather than doing the close down at this point is I'm going to take an offcut or a scrap piece of glass that clearly you can use many times. And I'm going to stick both of these in the flame and begin heating them. Now you'll immediately start to see an orange color from the glass. As that orange begins to transition to a yellowish hue, the glass is beginning to soften. So you're looking for that yellow color in the flame, not just the orange color. And when I now touch these together, they're sticky. And if I rotate this just a little bit to make sure that I have a relatively straight connection, now what I can do is I can move up just a little bit in order to be able to get the thing closed without wasting a lot of glass from my primary tube. So now I'm going to put this back in the flame and begin rotating this. And the trick is now my hand that holds the offcut is going to draw out of the flame. I'm not going to move both sides in or out. And what I end up with is a little hot bead of glass at the bottom. Before it cools, I take the graphite and I just flatten it slightly. The reason for flattening the end of the tube is optical. In order to get the LED light in, I want a flat surface to which the LED light is going to expose. If I have a, let me just put this down here for a second. If I have a round LED lens and a rounded tube, a lot of the light is going to spill out. But if I have a flat end of the tube, that round LED light, almost like an optical setup, will send the LED into the tube. So that's the reason for flattening the bottom of the tube. Now the next step is, if anybody is familiar with trying to heat up water in a microwave, say in a glass measuring cup, a Pyrex cup, or doing distillation where you boil liquid inside of a smooth glass container. The liquid inside can actually superheat, go beyond the boiling point, and then eventually it gets to the point where it can't hold off any longer and it does this sort of explosive boil. We don't want that. We want to give the bubbles a lot of surface area inside the tube to create tiny little niduses of initiation for vaporization. So we're going to add a granular material to the bottom of this tube that will provide those sources of boiling initiation. Now, in theory, you could use salt. This is a kosher salt. You could use rock salt. You can use Himalayan pink salt. You could use boiling beads. These are actually designed for just this purpose, little Pyrex beads that are designed to sit in the bottom of a flask and provide that additional surface area and prevent that explosive boiling. My favorite for this particular application is to use boiling chips. These are a rough aluminum oxide particle. Looks like this. They're white, so the light is able to transmit around and through them in order to get up the end of the tube. But they have a tremendous amount of surface area and produce a much better boiling. So we're going to put some of these in the bottom of this tube here. And this is often a little messy. I'll see how well I can do this time. And we have to do this now, as I'll explain in just a second. You'll see why. We'll see if we can feed a few of these into here. And in this case, less is more. You don't need very many. We found that every time we reduce the number, it just gets better. That's plenty. The reason I did that at this stage is in order to seal the tube. Oxygen off, flame off. In order to seal the tube like this, we have to narrow the tube a little bit because we're going to try to seal this under vacuum. If we try to seal this once we apply a vacuum from the full diameter, we get more failures. And it's much better if you can hourglass the tube before you do that. The problem is once you hourglass the tube and narrow the diameter in order to provide the seal, you can't get the chips in. So that's why we put the chips in at this point, and once this is cooled off enough, then I'm going to come in here and I'm going to show you how we narrow the tube in order to be able to do the final seal. Okay, so now in order to do the draw, what I did is I lined up these rollers and this little undersized post so that when I put the rod in here, it operates sort of like a very poor man's glass blowing lathe. When we do the draw, it'll keep everything nicely aligned. Makes the next steps a little bit easier. Now, this process here, because we have very primitive setup here for glass working, needs an assistant. So let me light this flame. And I'm going to ask Paul to come in here to help us because he's substantially better at this than I am. So what's going to happen is he's going to get himself all set up and ready to go, and then when he tells me to hit the flame, I'm going to go ahead and provide the heat.
All right, go for it. Stop.
Nice. Now what we're going to do is just let this cool. Now this hasn't had enough time to cool, so what we're going to do is add the dichloromethane. Now, when adding this, you have to be somewhat slow in the process because if you go too fast, it'll tend to overfill up here because this is working sort of as a very tiny little funnel. So we're going to fill this up and we're going to do it relatively slowly. And as we do, you can see the level in the bottom of the tube rising. We don't want to fill this all the way up. If we fill it up too high and we don't get enough space at the top, there's a couple of problems with that. One problem with the space at the top is that, with no space at the top, is that there is very little volume to the vacuum that we're applying above here. And with a very low vacuum, with a very low volume, you don't have a lot of reservoir of vacuum. So when you do the seal, even a tiny, tiny leak in the apparatus during the sealing operation can cause the vacuum to completely disappear. So you give yourself sort of a little bit of a savings account by simply having a little bit more volume above the tube. The other reason is that this is a heat transfer loop. It's not just the heat at the bottom, it's the cooling at the top. So if you provide a little bit more tube length to the top, you'll provide more cooling and this will operate better. Okay, so this is filled up pretty well. So now what we're going to do is hook this up to the sealing apparatus. Now because I've got the dichloromethane in here, I can't turn this on its side to seal. I have to do it vertically. So we took a ring stand here, put a little custom bracket on the side, have a little ball bearing mounted at the end of the bracket, and then I've made these inserts, simply drilled a hole in a piece of graphite that fits around the outside of the tube and will go into the bearing to provide us support. In order to connect this up to the vacuum, I'm going to use a little lab trick, and that is isopropyl alcohol is an excellent lubricant between silicone tubing and glass and makes it much easier to place the tubing on the glass surface. So I put the alcohol on the outside of the glass, I don't put any in, and then I can feed the rubber tube over the end like this to provide not only a seal but a lip. Now when I place this inside of the graphite like this, now when I place this over the graphite like this, it will hang from the graphite. I can then insert this whole tubing into the support like this, and we can then easily rotate this during the sealing operation. Now I'm going to hook this up to the vacuum up here, and this vacuum tube goes all the way down here, all the way across the table and over to that large vacuum valve that you see right there. This is in series with the tubing and the inside of the tube here, and measures the pressure that is somewhat regulated by this tiny little needle valve located behind here. So let's go ahead and turn on the vacuum pump and begin getting rid of some of the air. Now this is our old Welch dual seal vacuum pump. Really like this old guy, and you can see hooked up in series with the vacuum pump is an activated charcoal filter. That activated charcoal filter will absorb the solvents that are being pulled out of the tube and will greatly extend the lifetime of the oil inside of the pump. You don't have to go to Fisher Scientific and buy a $150 filter. You can get a little $8 or $9 filter for an RO system, and it works great. You get much more longevity out of your oil. Now, I've opened this valve just a tiny bit, and if you look at the gauge right here, you can see that it's beginning to create a bit of a vacuum. We want to do that very slowly because not only are we trying to remove the air above the level of the liquid, but we're also trying to outgas and remove some of the dissolved air that's in the liquid as well as in the porosities of the boiling chips. So we want to do this slowly. We want to get as much air out of this as possible. So at a very low pressure, usually as little as maybe a quarter of a full vacuum, in other words 3/4 of atmospheric pressure, we'll begin seeing a few bubbles here. And those bubbles are not dichloromethane bubbles. Those bubbles are air bubbles. And you can tell the difference because the air bubbles will actually expand when they get near the top because the pressure is obviously going down. So we'll give that a little bit of time to do its outgassing. You can see some of those fine bubbles beginning to rise. You'll get a much better result if you're patient. Now this operation is also going to require an assistant. So once we've got the pressure down where we want it, which is about 1/2 an atmosphere, we can't get any lower because any additional attempt to try to draw the pressure down simply boils away more dichloromethane and we'll never get any better. So once we get to about 1/2 an atmosphere, we're at about the vapor pressure of dichloromethane at room temperature, we're ready to go. Now the reason for this thin tubing up here is that in order to be able to seal this, we have to rotate that tube. So we're going to have to free ourselves up from the vacuum system. And a very easy and convenient way to do that is once we get down to that pressure, we're going to kink this tubing, put this little paper clip on the tube, and then we're free to be able to do the sealing. I'm going to go ahead and light the torch and get ready. Now by clipping that off, we've freed that from the vacuum system. We can now pop the connection. We still see the bubbling, so we know we have a good vacuum. And I'm going to place the torch just slightly above the narrowest part of the interface. And when I get the go-ahead, I'm going to start heating.
Go ahead.
It's that easy. Now you see that little spicule of glass on the end of this. The easiest way to get rid of that is simply to hold the flame steady and allow your assistant to effectively melt it back to the tube to make it a lot less vulnerable. And as you can see, we're still getting bubbles in the bottom of the tube. So we've got a good vacuum. This is going to be a good tube. All we have to do is let that cool for a little bit, and we'll be able to work with it.
Okay.
Just hand heat.
Do you want to demonstrate it in your hand?
Well, I could. My hands are always hot.
That was stressful because this thing right here.
It wasn't rotating that easily?
It was, but this thing is going to need some grease or something.
Yeah, I might just loosen it a little bit.
Just add a little bit more grease in there.
Okay.
Because what happens is it turns perfectly as long as you're going perfectly straight down. But if you go at any bit of an angle, even a little bit, so if this thing isn't perfectly straight and it's got a little wonk to it, this thing wants to lock.
Yeah.
And so it was hard for me to, it worked, but it wasn't ideal.
Well, I'm glad you were doing it. So let me give you a little bit of an overview on the mounts. They're really straightforward, but maybe some tricks or techniques here might help to save you some time if you're going to do this. In order to provide a relatively stable base, you want some mass at the bottom. And so I took some aluminum rod, simply cleaned up the outer surface, and then bored a hole in the top surface that matches the hole of the diameter of the tubing. What's nice about this tubing is it comes in nominal sizes, like 8 millimeter, 10 millimeter, 12 millimeter, or half an inch, quarter inch, 3/4 of an inch. And so what you do is you simply buy a drill bit that is the same as the diameter of the tubing. Anytime you try to drill a hole with a typical drill bit, you're often going to get a couple of thousandths of clearance. It's usually not perfect, and that's enough clearance for these tubes. So simply put this in a drill press or just use a very, very good handheld drill and drill a hole that will provide the mounting point. And then what you'll do is you'll put a little bit of a thermal grease, like our thermal grease, to act as an interface between the heat and the tube in order to get the heat into the tube. If you turn this over, you can see that we've counterbored the inside of the tube to a 1-inch nominal diameter. In that little bit of an inset, or that counterbore, what I've done is I've taken some 1-inch aluminum rod and simply ground the edges. You can put this in a belt sander, or you can use a mill if you've got one. And you want to make some flats on either side of this 1-inch diameter tubing or rod to allow the wires from the LED to be able to get past the rod. That way you can insert this into the bottom of the mount, and this can then be fixed or supported or held in position by either using a little bit of a UV curing adhesive, or better yet, maybe just a little RTV silicone adhesive. Easy to remove if you want to remove the insert, but at the same time it will help to support this, because the lamps themselves will actually sit on the LED, and so you need a little bit of support. These LEDs have a protective lens on top of them, so they are perfectly safe to mount and support even the largest tubes that we have. They work perfectly fine. These LEDs are from Cree. We bought them from Rapid LED, but Cree manufactures a variety of different colors and brightnesses. They make a deep red, an orange, a green, a blue, a deep blue, and even UV and white. And so you can get whatever kind of color you want in the LED, put it onto the insert with a little bit of a thermal epoxy, like our thermal epoxy, and then just weld the connector wires onto the side. Now, in order to get the heat into this, what I did is I fabricated some resistors as heaters. And to do that, you measure a diameter about halfway between the insert and this little ridge that's going to act to support this on the table. Then multiply the diameter by pi, and you can get the fabricated length that you need out of a series of resistors. These are 3 watt, 3 ohm resistors for a total of 12 ohms of resistance. Then once you've soldered these things up, just take a little needle nose pliers and begin to bend this into a circle, like I've done like this. This allows you to put this inside of the base like that. And then to make sure that you get good thermal contact, you want the LEDs or the resistors to sit flat against the aluminum. Take a little bit of a UV curing adhesive, put a drop against one of the resistors, take a UV light, and simply cure that. 5 seconds or so, go around to the next one and do the same. The reason you're doing that is that when you bend this ring, you often don't do a perfect job. It often is not perfectly flat, and you want these resistors to sit flat. Once they are temporarily mounted with the UV adhesive, then what you do is take a little bit of a thermal epoxy, like our thermal epoxy, and drip it in around the resistors to provide a good thermal interface with this material here. Now, I've wired these up to be a 12 ohm resistance, and when run in series with these LEDs that all operate well at about a 0.5 amp, you'll find you'll get about an 18 ohm total resistance, so that you can actually wire this all in series, the light to the resistor to a power source, and you can drive the entire apparatus with a 9-volt wall wart. So very convenient and compact. So that's basically how you build one of these bases, and the tubes, I've shown you how to do that. Now let me show you how far you can carry this process. Come on. So as you can see, we've done a large number of these. We've actually done a few more and are working on even bigger ones. But what's nice about these custom lights is you can make them in a variety of lengths, obviously, in different diameters. These are the thin diameter tubes, these are the medium sized tubes, and these are our larger diameter tubes, the 18 millimeter tubes. Because you can add different LED lights, you can create different colors. And you'll even see some other subtleties in here. For example, these are the glass boiling beads and produce a substantially different type of bubble. But in all of these cases, what you can see when the bubbles rise toward the top surface here, they dissipate and basically have recondensed by the time they get to the top of the liquid, which is kind of neat. These things look like little Pac-Men going up to the top and then eventually get compressed like pancakes. These tubes over here are a little bit different, and we'll get into that in just a second. One of the things that I like about these tubes is the sort of custom or handmade nature of the little sealed ends, these little, I don't know, ice cream cone type ends that we formed, the little meringues that we formed at the end of the tube. But if you want something a little bit more robust or a little more finished, you can get these black soft rubber caps that are often used to cap off the end of pipes or tubes. You can get these from McMaster Carr. They fit the nominal diameters of these tubes, and you can place them over the tube with little RTV adhesive like this, and you can create a little bit more finished end to your tube if that's the way that you would like this to look. It's up to you. You can do it however you want to do it. Now, in order to show you some more interesting upgrades that we've done, let me turn the lights on in the room and show you what's going on over here. It's a little bit different. Now, as I said, you can get these LEDs in all different colors, and what's unusual with these lamps over here is that we're using, obviously, white, which produces kind of an interesting pattern. I thought this would be boring, but it looks more like mercury, so it's kind of neat. The white is better than I thought it would be. But in these 3 lamps here, we're using UV, invisible LEDs, that are driving dyes that, in this case, this is our strongest, most fluorescent dye. We are actually causing the dye itself to glow under the UV influence. For example, if you take one of these solvent dyes, this is a green solvent dye, and if you add just a tiny quantity of this, just enough to coat the stick with the dye, and place it into the dichloromethane, you'll get a brilliant green color that fluoresces under UV light, like this. This is basically laser dye. Pretty neat, huh? And that's what's happening in this tube over here. What's nice about that is that the light itself doesn't show up, only the fluorescent dye. And so as a result, this tube uses one of the other upgrades that we decided to experiment with. The dye itself does not dissolve, this is a solvent dye, in water. And so on the top surface of these three tubes, we've actually added about half dichloromethane and half water. The fluorescent dichloromethane dye is heavier than the water, and so the water floats on top. What's neat about that is that as the bubbles come up, and it's best seen over here, the bubbles will continue to rise up to the surface here through the water, and they will accumulate the liquid at the top, and because it's heavier but held up briefly by the surface tension of the water, they will then plow back down into the dichloromethane almost like a lava lamp. It's a really neat kind of addition that you can do with this kind of setup. Now I've got this over here to a low heat setting. This is medium and this is a high heat setting. So even by adjusting the heat, you can effectively adjust what's happening to these bubbles as they're going up through the water. Now, kind of a little bit of a tweak or a riddle for you chemists. You might think, how can you be getting dye at the top surface over here when effectively this is a distillation? The only thing that's inside of those bubbles is dichloromethane vapor. It can't be containing the dye. How does the dye get up here? What happens is when the dichloromethane bubble reaches the interface point, it is surrounded by a dichloromethane liquid. The surface tension forms the bubble. When it enters the water, because it's not miscible in the water forms a secondary membrane over the dichloromethane bubble. And so the bubble itself will actually carry a tiny bit of the dye up along the outer wall of that bubble, up to the upper surface. And then eventually will come back down. So you can probably trick your chemists friends about this if you ever decide to build one of these. And that's basically it. You can play around with all different types of colors. You can play around with different types of dyes. They make a variety of different fluorescent dyes. And so you can really have a lot of fun by just mixing and matching. And because of the modular function of this sort of a setup, you can mix and match different lights. You can change them around. And it produces a really interesting display. Now, we built these and actually have built several more of these. And so what we decided to do, in keeping with the holiday season, is we decided that what we're going to do is we're going to take a drawing from some of our Patreons, the people that have supported us through the years. And we're going to send some of these fluorescent bubble lamps to them as a gift, as a thank you for all the support that they've provided. So you might get a little notification from us that we're going to be sending something forward to you. So keep an eye on your Patreon account or your email, and hopefully you'll get something relatively soon. We're not obviously going to be able to satisfy everybody, but hopefully we can get a couple of these out. In any case, I hope you found the video interesting. It was a lot of fun to build. We've got a lot of these things around. We're going to be building some really huge ones, so it's going to be a bit of an adventure going forward. And if you have any questions, do you have any comments, put them down in the comments section below. It gives us ideas for new videos. I read them all, and if there's any questions, I try to answer as many questions as possible. But stay safe, have fun, enjoy glassworking, enjoy a little bit of very simple chemistry and physics. You have a wonderful holiday season. We'll see you soon. Good night.